Hello students, in this video I am going to go through the process of deriving the equation for an ellipse. Now, to be honest with you, I'm not 100% certain on the history of this topic, what was the scientific discovery, okay, that led up to this derivation. I'm sure that if you look into it, that it would be a very, very interesting story, and it will be actually a very involved story because I'm sure it's not going to be a short segment. This history and the series of discoveries and the people involved. Okay, I'm sure it's going to be very extensive. Just as you will see, what we're doing here in this video is a part of something much bigger. Okay, part of a set of equations that you're going to discover in other videos that I'm going to make, okay? That this is actually a small peg in what is a giant gear and a part of a bigger machine, okay? What exactly is an ellipse? So an ellipse, okay, is actually the shape of an oval. I'm sure the history, okay, behind this had something to do with astronomy, where the discovery of the motion of planets. Okay, as it turns out, the motion of planets around the sun is not orbiting in a circular manner, or satellites for that matter. Okay, things that orbit in space actually orbit in an elliptical manner, and the rule or the geometry that governs the motion of the planets, okay, is that the ellipse actually has two focus. Unlike a circle where the center, okay, is the main focus of all the points, okay, on the circle, here we have two foci, okay. So what's the significance of having two foci? Well, as it turns out, the distance between any point on the ellipse to either of the foci, the sum of those two distances must be the same all throughout the different points on the ellipse. So what do I mean by this? So for instance, let's say we have another point over here. Okay? The distance that point is away from the focus on the left, when added with the distance of the focus to the right, the sum of those two distances in green must be the same as the sum of the two distances in blue. So again, to find out what that constant is, between the two distances, what we need to do is then think about this in its extreme. So what I'm going to do is take a look at this extreme here. Let's say I have my point here on the right, okay, the far right. The length of that green line is going to be a minus negative c, or in other words, it's a plus c. The distance between the rightmost point and the right focus, okay, will be a distance of a minus c. So therefore, the distance, or the constant, okay, that is d1 plus d2, all throughout the ellipse must be a length of 2a. It doesn't matter where you are on the ellipse, okay, the sum of d1 and d2, no matter where you are, will always be 2a. Now this is going to be the rule that defines the geometry of the ellipse, and this is how we are going to then be able to generate the equation of the ellipse. So based on this, okay, I'm going to write out the distance for d1 and write out the distance for d2 for any point on the ellipse. So the distance for d1 is going to be square root of x minus negative c squared plus y minus 0 squared. This is finding the distance between x, y, and negative c comma 0. I will do the same thing to find the distance of d2, which is point xy to c comma 0. And the sum of these two things will equal to 2a. So what I'm going to attempt to do in the next couple minutes is to rewrite this equation in to something that looks a little more manageable, a little more elegant, okay? Technically speaking, this equation here is the equation of the ellipse, but this is not accessible just because it looks really jumbled, and we need to get our thoughts together a little more coherently. So what am I going to do? I'm going to reduce the equation down a little bit, okay? I'm going to perform some simplification. So immediately y minus 0, that's just y, right? So we're going to square that, so we get rid of the zeros. Something else we can do, okay? We can attempt to get rid of the square roots. How can we get rid of the square roots? Well, in order for us to get rid of the square roots, we'll need to square both sides. And in order for us to square both sides, it would be advantageous for us to bring one of the square roots to the other side so that when we do square things out, we'll we can apply structure to it, okay, and have the algebraic expression look a little more manageable. But regardless, we can square both sides at this point either way. We'll still end up at the same place, but I personally like to bring one of the square roots to the other side and then square. So I'm going to square both sides from this point, and if I do, I'll end up with something like this. I'm going to apply structure now to try and FOIL out the right-hand side. And immediately from here, you can see that we have y squares and y squares here that they will cancel. I'm not going to do that just because I see that there are actually other things that will cancel. That is only after I FOIL those, again, by using structure to FOIL it, right? So those things that I highlighted in blue, those are perfect squares. So I am going to figure that out. That's x squared plus 2xc plus c squared, right? And then from here, it is clearer now, okay, that I have more things that I can cancel. Certainly the y squares will go away, the c squares will go away, the x squares will go away. I can then also combine the 2xc's in my next step and bring over the 4a squared. And then at this point right now, okay, between the left-hand side and right-hand side, immediately see there's a common factor of 4. I'm going to divide both sides by 4, but actually not just 4, I'm going to divide by -4. Notice that when I divide by negative, the order of the subtraction there, I reversed it. That is going to be a quote-unquote trick, okay, algebraic trick that you should be familiar with, okay? So at this point right now, okay, I am pretty much primed to square again. I'm going to square both sides to try and get rid of that square root once again. And at this stage, okay, now that both sides are squared, I'm going to FOIL out the right-hand side. I mean, not the right-hand side, the left-hand side. So I end up with this step now. From here, you should be able to see that, again, there are going to be more things we can cancel the moment I distribute the a squares through. And then from here, notice that there are a squared, 2a squared, xc's on both sides. There is a, and then there are, and then that's it actually. That's all we can combine or get rid of. So I get this, okay? I do notice one thing, okay, that I have really two types of terms here. I have terms involving a variable, and then I have terms involving just constants. Remember, A and C here, they were the, A was, what was meant by A again? A was the extreme, okay, of the ellipse, right? It was one of the vertex of the ellipse, and then C, okay, was the focus of the ellipse. So those are actually constants. What I can do is I can combine the constants, and I can combine the terms with the variables x and y's. So that's what I'm going to do. I bring over all the terms that involve only constants to one side, which is what I have here, and I bring over all the terms, okay, that involve variables to the right. Between the first two terms on the right, there is a common variable of x squared. I'm going to factor that out. And by doing this, you're going to see now, okay, that this and this, okay, have something in common. There's a common factor of a squared minus c squared. And this part here, okay, it just, like, how did the person, discover this equation, like, know to do this or to write the equation in this manner? Some of it has to do with like inspiration and then on the other parts has to do with experience. Okay, I would have to say people generally will recognize like quote unquote tricks or ways of re-representing things algebraically to make it look nicer, and this is largely due to like a ton of practice and a ton of like exposure to working with algebra and manipulating algebra. Okay, so what we're going to do, okay, the next step is divide both sides by a to the fourth minus a squared c squared. Why am I doing that? Because in the next step, you're going to notice that the denominator has a common factor of a squared minus c squared with the first term, and the second term has a common factor of a squares. So the whole fraction then gets to be rewritten into this expression here. And we are really in the home stretch because this equation in green right now, doesn't that look a whole lot better than the equation that we started off with? It does, doesn't it? We can do even better, okay? And why is that? Well, that's because there's one other piece of information that we have not used since the very beginning of the problem, and that was, yes, this is the one extreme, okay, on the vertex, on the ellipse, but there's the other extreme that we have not used yet, okay, and that is this 0, b here. And we're going to use that right now. So when x is equal to 0, the y-coordinate has to equal to b, right? Since 0, b is a point on the ellipse, then, okay, if I substitute 0 in here, the y-coordinate here has to equal to b. So therefore, the result is I'm going to end up with this equation. One more time. When x is 0, this term goes away. I'm left with the equation that I have down here that's in green. Why is that important? Well, this relationship is telling me something else. This relationship is telling me that b squared is equal to a squared minus c squared, because if I multiply both sides by a squared minus c squared, that's the relationship I end up with, right? So what's my final step? My final step is this, that the equation of an ellipse centered at the origin will have the equation x squared over a squared plus y squared over b squared equal to 1, where b squared is equal to a squared minus c squared. And this is the derivation of the equation for an ellipse.